doesn't just go to Go Fish or Synchronization on Android devices. Richard and I both came to Professor Lowrie with an idea for an Android app called Music Pals. We just both spent the summer working on mobile apps, and we came up with this idea that was essentially a chat app that allowed users to chat but also listen to music at the same time. And what makes our idea cool is that you can think of everyone at a party listening to the same song with their headphones on. And so they all have the same song at the same time, they can all be enjoying the night. But also imagine if you unplug those headphones, then you'll have a surround sound party where every phone has the same song. It could sound really cool. But there's a lot we had to do.
So the first step was to figure out a way to connect these devices. And the first technology we looked into is known as Wi-Fi Direct, which on Android is called Wi-Fi peer-to-peer. And what this allows you to do is connect devices directly to each other without the need for a third party. So you can think of it like Bluetooth. So there's no server, no router involved. And how it works is one device sets itself up as a host device, essentially an access point, which broadcasts an SSID, and then other devices can go ahead and then connect to it. And we found this was great for point-to-point communication, so one host and one peer. But when we started forming groups, we noticed that the functionality was lacking. And Don's going to talk a little bit about us turning to a server, and thanks to Professor Ames, we took his mobile apps class and used a lot of his demo code that he showed us there. So Don's going to talk more about that.
Okay. So yeah, as we said, we couldn't really crack the multi-phone groups working. So our first idea was to have a server running on my MacBook, and what essentially happens is phones can connect in, and we can make groups with the phones. And so we had the server handle users for each phone, and you can request a chat with various users, and they put them into groups. And we handled multi-groups at the same time. We were pretty proud of how it all worked together. We could have different chats going all at the same time. And there's just a little bit of code that showed kind of how you can send messages in and read them back out through each of the sockets that are in each of the groups. But we moved on, and we wanted to take it one step further and put the server on a host phone. So with that, it takes the computer out of the equation altogether. And I made a quick Go Fish app that demonstrates how we have essentially group chat running off of one server phone and other phones. And so essentially right here, I have my host phone in this big Samsung Galaxy Mega, and I will start a server. And up here, this right here is the IP address of the host phone that I'll connect into. And so we got Dom and Rich connected in. And as you can see, what happens is if I send a message in, it goes through the server, it gets sent back out to everyone who's connected in the group. And as I said, I created Go Fish. So we'll deal 5 cards to Dom, 5 cards to Rich. And the deck is stored on the server phone, and it just has a method to handle the deal, come out how many cards, and send it back out to the individual phone that requested them. But moving on with Go Fish, we can ask Richard, do you have a 7? And as you can see, Richard gave up his 7, and Dom gets to go again. Well, let's try again. 2. And he doesn't. Richard did not have a 2. And if you count up Dom's card, which are really organized in the correct fashion, he will have now 7 cards. And that's essentially the app. I didn't take it to completion, but it really shows how the server handles the the chat and how we can have methods within the phone to handle certain messages that come in and on the server to handle certain messages. So we'll go back and, with this server code, we actually did finish making music files. We used Spotify to handle tracks. So you could send to your group, let's start track number 7, and all the phones would then play a song through the Spotify API. But we noticed we had another issue, which was syncing up the times in which they start the phones, which Richard will talk about now.
Right, so as Dom said, we noticed, for example, on the devices, if we said, let's all start playing a song at noon, exactly at noon, we noticed that there would be some delay between the devices, so they would not all be exact. So their internal clocks were all a little different. So we wanted a way to sync up all these internal clocks on each of these devices to make sure that they were all on the same page. And we use the network time protocol to do this. And this protocol allows you to ping a server. That server then returns the time. And then, based on that, you can see this code snippet down here, we get the offset. So the offset right here tells us how far off our internal clock is. So let's say my phone is 100 milliseconds fast. This offset will be -100. So it needs to correct my internal clock by, slow it down by -100 milliseconds to sync it up with this NTP server. So that's what this line's doing right here. And we noticed that when pinging these, the NTP server, that sometimes there would be outlier values. So what we're doing is we're pinging it 3 times, and any value that is too far outside the mean, we just simply toss it out. Because when we're dealing with audio synchronization, every millisecond counts. So we want to make sure that we have the most accurate sync time possible. And we also noticed that we had to constantly stay in sync with this NTP server, because even just over a minute after we synced up with the NTP server, the offsets would change on all these devices. So Dom's going to talk a little bit more about what this time drift kind of looks like over time.
So the idea of time drift is, when you buy a really fancy watch, you sync it to, whatever time zone you're in, and you hope your Rolex will be on that same time a year later. But what we've noticed with Android phones is that they do not work at a steady rate. Android has a built-in feature where it corrects, what mistakes it has going day to day. So you look at your 2 phones, they'll switch from like 12 to 1201, but that's because they're constantly syncing up. But for the sake of our project, we needed to make sure, that we synced it correctly with the NTP time. And what this graph here illustrates is we turned off that auto sync of time that the phones have and just let them run for a while and saw how far they got off from essentially the NTP time. And this is run in the course of 2 to 3 days. And as you can see, the Nexus 4 is, 21 seconds off. So this isn't going to work for us. The other interesting point is noticing that they're not, on a parallel line, which essentially would have helped our project as well. If they were all running at the same rate, it would have been great, but they're very far away from each other. So what this all boils down to is we have to constantly ping NTP, the network time protocol, to get time synced up a lot more than we initially thought we would have to. And there was one final issue we had, which was how long the device actually takes to run the code, and Richard will talk about that now.
Right, so as Dom said, syncing up the time is only half the battle. It doesn't mean anything unless you can actually then go ahead and play the audio exactly at that time. So we noticed a couple issues. So here's some demo code, which is actually from a demo we'll show at the end of the presentation. You can see right here, we're creating a new handler, and a handler on Android essentially is an object that allows you to post runnable objects to the thread that created it. So you can see that the main thread is creating this handler. And here's just a simple runnable object that is just animating a text view. This will make more sense when we show you the demo. And this is the post delayed method we're calling on the handler, which allows you to execute the runnable object at a certain time into the future. So this delay milliseconds value right here, you can imagine if we pass it in 3000, that would play 3 seconds into the future. And it's important that this is as accurate as possible. because if it's not, it's very glaring to the user. And we noticed that on older Android devices, which are those running the Dalvik runtime, this is the runtime that shipped originally with Android. Since then, they've switched to the Android runtime just as of this past year. And we noticed that the Android runtime introduces a lot less latency when scheduling things with handlers. So that if I schedule something to be done 3,000 milliseconds in the future, the Android runtime gives us a lot better, does a lot better job of doing it, whereas Dalvik is not as accurate. And also, there's Android's 10 millisecond problem, which is that it cannot process audio in under 10 milliseconds. iOS devices can do this, which is why there's a lot of professional audio grade software for those devices, but this type of software is lacking on Android simply because there's this 10 millisecond problem. So essentially that when we start playing audio on an Android device, there's inherent lag before it will actually start playing. And not every device has the same amount of latency. It depends on the hardware of the device. So that's a difficult issue to overcome, and it's something that a lot of developers are none too happy about. So Dom's gonna talk a little bit more about, okay, where can we go from here while I set up our final demo, and then we'll wrap this up.
Okay, so this demo is going to make a little more sense. We have music and a display running at the same time, and we were thinking, what can we do with this in the future? And one of my ideas is imagine, a bunch of people in a crowd. Instead of holding up a lighter, we could all be holding up our phones, and displays could be, synced to the music. You could have a really cool light show in a concert. But with synced up displays, you can do cool things anywhere. Imagine in a football stadium, all these devices, screens can make a large screen, which could be very cool. The final idea that we're toying around with is the idea of filming events or whatever from multiple phones, because if we have their time synced up, we can get the video synced up as well.
So yeah, let's get this started here.
And here's our accumulation of our work.
So we'll walk up and we'll hold these devices next to each other.
These devices right now are calculating, pinging NTP and syncing up their times as we speak. And
we do one final calculation here right before the event starts, so we know that it's as in sync as possible with these with the time. So we can all remain quiet. Let the music kind of go. So you can see we're doing a couple things here. Yeah, turn the volume up. So we're syncing the animation, and we're syncing the audio. And again, these devices are not communicating at all with each other. This is all done by connecting to an NTP server, syncing up their times as close as we can, and then this is just an example of what you can do. So we sync up the lyrics a bit. So.
Yeah, we'd like to thank Professor Lowrie for helping us, guiding us through this throughout the year, and it's kind of
There we go. Yeah, thank you very much.
Just have one quick question while the next presenter starts heading over.
We answered everything. Thank you.